Nathan. This past year, I was team lead of Rensselaer Motorsport. I got involved my freshman year, and this is now my third year on the team. It's really been, for me, kind of one of the biggest parts of my time at RPI. So I really hope that for a lot of you, it can end up being the same. So just to start off, we're going to show two quick videos. One of them is the car running. It's kind of an onboard video. And the second one is a video that our marketing team made, kind of showing one of our weeks just hanging out in the shop doing work to give you a sense of what it's kind of like. So this first video here is kind of explains. That's the car. And then the second video is just kind of a week in our shop. All right, so we'll have other people who are part of this webinar today join in, introduce themselves, and then we'll get started with talking about the car. Kevin, if you want to introduce yourself.
All right, we'll wait for everyone else to broadcast. So yeah, my name's Kevin Zanita. So I am a senior now. I'm graduating, but I'm a computer and systems engineering and computer science. I've been on the team since my freshman year. I served as project manager for the engine drivetrain and electrical subsystem for 2 years. I was also electrical specialist for a little bit. Yeah, so that's me. Nick, if you want to.
Hey guys, I'm Nick Jones. This past year, I was the chassis suspension and aerodynamics project manager. I am a sophomore going into my junior year at RPI. I joined at the beginning of my freshman year, and since then I've been working a little bit with aerodynamics and composites, and with the chassis and suspension side of the team.
Hi, I'm Katie Crawford. I'm a senior studying mechanical engineering at RPI. I've been part of the team since the spring of my freshman year, and I've done a bunch of design work for the engine, drivetrain, and electrical side of the team, and I've been elected for next year's ED design lead position.
Justin?
Justin might be frozen.
All right.
Hi, everyone. I'm Sam. I'm a second-year information technology and web science student. I've been involved with the team since fall of my freshman year. Served as CIO for about a year and a half, and I'm the team lead elect for next year. And I've primarily worked on the car on electronics components, so things like wireless telemetry or strain gauge modules or that sort of thing.
You're quiet. Yes.
Justin, you want to go for it now?
All right. Here's Justin's added twice.
No. Can you guys hear me?
I just heard you, Justin.
Can you hear me now? Okay.
No, just
Hi
talk.
everyone, I'm Alex. I am the business manager for this past year. I'm a senior mechanical engineering student, and I'll be coming back in the I'll be coming back next fall for co-term. So I'll probably be around the team as well.
All right, well, that's a quick introduction as to who we all are. I see there's a couple questions that have popped up in the chat. So first, does your team build a new kit every year, season, or continually update previous ones? So as we'll get into, every year we pretty much design from the ground up a new car and build it, and then bring it to competition at the end of the year. But we'll get into a lot more detail as to kind of just what that entails. And to the person who said that motorsport was the coolest sport in the world, I have to agree with you. I think there's quite a few of us who agree with you, and you would definitely find that you are at home. So a general overview of what we do each year. The year starts with a lot of design work. So as you mentioned, there's a new car, pretty much a ground up new car every single year. So that means
can you guys hear me?
Starting just after competition the year before, design work on the new car begins. And that generally covers 6 main areas. So engine work, drivetrain work, electrical work, chassis, suspension, and aerodynamics. And in order to do this, we use a lot of different techniques, everything from kind of basic hand calculations through to computer modeling, using tools you've probably heard of like FEA and CFD, which are finite element analysis and computational fluid dynamics, which basically lets us break things and have a virtual wind tunnel to predict the behavior of the car and parts on it. We build all the wiring harnesses from scratch and design all of that. All the composite work on the car is stuff that we design and build for the most part. The whole chassis, we do all the welding, all the fabrication for that. But more and more, a huge part of the year is either developing software to predict the behavior of the car. So Justin actually built a lap simulator last year to help us kind of predict the effect of changes on the car. as well as developing software for things like stability control, traction control, things like this to make the driver's life easier. Once we get into the later part of the year, April, May, testing is really the name of the game. And it's unfortunate right now with this pandemic, we are all kind of stuck at home and testing is not happening. But usually the biggest part of the year, one of the most exciting parts of the year, is seeing the car get out there, get running, and starting to kind of see the fruits of all the work that has gone in up to that point. And then around early May, we go to competition in Michigan, where we compete against about 120 other schools from around the world and try and win. So move on to the next slide. So generally, as a team, we're about 30 members who are full members and spend a pretty significant time investment working on the team, and about 20 volunteer members. We don't really have strict requirements for joining the team. We really want everyone who wants to be involved, and there's a lot of different areas to get involved with. So those are just kind of a selection of the people, the kinds of majors that have been involved with the team. But business majors, this normal kind of mechanical aero majors, all of the computer science and electrical engineering majors, there's a huge swath of different people involved in having the car come together each year. So generally the team is split up into kind of two different halves. CSA, which handle kind of the structural components of the car, and EDE, which handle making it move and go fast and turn on. As I mentioned before, every year there's a new car from the ground up. And somebody had a question, where do you guys get funding for projects? So most of our funding comes from external sponsors. And it's the responsibility of everyone on the team, but also the business team plays a huge role in that and kind of managing those relationships that we have with sponsors so that we can keep coming back to them year after year and get support from them, as well as hopefully provide value to them as well. I guess I'll go through a couple of the other questions here. Somebody asked, how does someone join the team and how's the driver of the car chosen? So joining the team usually is the beginning of the year, show up to events. There will be like new member barbecues. We show up to the activities fair and just talk, find out more. And then we'll have some days where you can like show up to the shop and learn a lot more about the team and when we meet, etc. We don't really have a specific set of requirements to join. It's really, if you think you have something that you can offer or you'd like to learn, then by all means. Mark asked, do motorsport and hybrid work together often, or are you entirely independent? So for the most part, we're entirely independent. We both compete in different competitions. So although there's a fair amount of crossover in the fact that we both build cars, they are actually very different competitions, and the goals are quite different. So there isn't a huge overlap between the two teams. Yeah.
To answer Melanie's question, no, you don't need to know about cars. Just as much as it's a car application, it's as much an engineering experience. So if you're excited about engineering and you're excited to learn about how things work, this can absolutely be the spot for you.
Absolutely. So that's a picture there of us actually, I'm hearing a lot of feedback. Katie, do you have your mic on?
I can turn it off.
I don't know if it's you, but I think it might be. So that's a picture of us from last year competition. You can see we're a pretty large group of people. That's the majority of the team, but not the entire team. And that was right after endurance, right at the end of the year. Everything was all wrapped up. And you can see comp is a very fun time. Definitely all end up pretty tired by the end of it, though. So moving on a little bit into more detail about exactly what we do. So I guess who's the best? Do we have somebody good to talk about engine stuff? I guess, Katie, you probably are reasonable to talk about engine development things. Unless you don't.
Well, I'm glad I'm reasonable. So a fun part about designing things is you get to design all sorts of different components. We tend to steer away from just buying stock parts and throwing them on the car because that's not how you get the competitive edge in racing. You really like to tear down the insides of how things work and what you can improve and what you can do better. So this year, one of our biggest improvements was high compression pistons for our engine. So we tore apart our Honda CBR 600 engine and put in some new parts in there. And so now we're testing out with design validation of different oil weights, different components, and seeing how that improves our max horsepower output and other gains in the car, such as weight management. So there's a picture of that situation where we have the head and the block separated. Next. So this is what our dyno stand can look like just for the engine testing. You can see on the left, that's our interaction with our engine tuning software and our units that are on the engine. You have this thing called your engine control module, and so it's basically like a computer on the engine. Your cars have it too, but we actually get to see on the insides of it and see what's actually making the car run. And then on the right, you see our dyno stand, which is the engine as it would have been in the car, but mounted on a stand that we fabricated instead. So that way we're able to run the engine itself while we're building the rest of the car behind that shot of whoever was taking that picture. So that's a good way for us to kind of do our design validation and our testing while we are also building our brand new car. And so that's a cool picture of what the engine bay looks like actually installed in the car. You can see from the bottom the intake, the fuel rail at the top of the picture, and at the bottom of the picture you can see part of the suspension system. And then there's the oil system all inside of it. So this is a really cool picture to show just how compact this thing is and how many different parts and pieces and subsystems go together. This is a good picture of, counting real quick, 3 or 4 subsystems. But probably more if you want to break it down to even more specific groups. So, and they're all on top of each other, and they're all in this really harsh environment, so you have to design for that. It's very cool.
All right, so we'll move on to kind of some samples. Obviously, can't show everything involved in making the car because there's just way too much to put on just a few slides. But these are just a couple samples of some modeling that we've done, some neat parts, and then on the next page we'll have some CFD as well. I noticed that Kevin asked, are there cuts if too many people sign up? Have you experienced this before? So no, we'd love to see the team grow and grow and grow. There's always more to do. There's always more that can go on the car. And so no, we don't have any limit to the number of people who are able to join the team. So I guess just looking around these 4 pictures here, in the top left, we have a finite element analysis model of a sprocket. The teeth aren't modeled in there yet because it's just kind of a preliminary strength analysis. Katie actually designed this. In the top right, we have a potential model for carbon fiber wheels. We developed some carbon fiber wheels for this year, but given all this extra time off, there's been a bit more time to go into more depth and detail on that. Bottom left, you can see our electronic throttle. This allows us to separate the inputs of the driver from the actual effect on the throttle, and so we can do a lot of things with kind of how the driver interacts with the car and how they get torque from the car to make it easier to drive. And then finally, we have a rendering of the chassis. So this is just one CFD model from the development of the aero on the car. As much as possible, we try and validate everything as much as we can in using CFD programs, and then attempt to correlate that to real life data once we actually have the car put together and built. But because these cars don't go as quickly as a full-size race car, they have crazy amounts of aero and huge wings in order to produce the amount of downforce to be competitive. And drag isn't really such a big issue. And so you end up seeing these massive aero kits that are quite exciting to see. All right, 3D printing. I guess, Katie, you're probably best to talk about this as well.
So we have an alumni at a company that makes 3D printers, and so we're able to do a lot of experimenting, both with rapid prototyping for machine parts and for actual parts that go on the car. There are plenty of benefits when you look at the different materials that are available to you and the different geometries you can accomplish with 3D printing, because they aren't as limited to tooling setups the same way typical machining processes are. So here's a good picture of a 3D printed oil pan that we have. And so we are able to actually, when we're printing, embed hardware into there to put the AN fittings into the oil pan and all the through holes for the bolts and everything. And so that's a neat way to look for these competitive edges when you're trying to trim down weight anywhere when you can on the car. And so there's an example of rapid prototyping where we printed the model of the sprocket so that way we could kind of see real time, make sure that the chain actually fits on the tooth profiles before we send this off to machine it, and just see what the part looks like in person. So now we're into the electrical section. So this is a fabrication stage for the wiring harness that we build. Kevin can talk more about that too.
Yeah, so I kind of worked on the electrical wiring harness for like 2 years before passing it off to Katie, who likes to work on everything. But yeah, so the wiring harness is a pretty big process, both the build and the design. The design is mostly figuring out, okay, what sensors, what actuators are on the car, because obviously you have things like the throttle body and the different sensors for like wheel speed and engine pressures and temperatures. So the wiring harness kind of connects all of those. Here you can see one of our pegboards. So we lay out the entire harness based on where everything is located and try to minimize all the distances, minimize the amount of wires we use, and try to cut down weight and routing as much as possible, because keeping it simple makes it a lot easier to work with. It's really an interesting subsystem. It takes a lot of work, but it's definitely worth it because you can get a really, really lightweight harness, and it's kind of really neat.
So here's a picture kind of the whole bundle coming together. So you can see that we have the actual wires there, and then they're held together with Kapton tape that can kind of resist the different temperatures and conditions that they're in. And it actually does something where you reduce the actual strain in the wires because you're holding them in place. They're not sliding together and creating more loads underneath the packaging that could break some of your connections in there. And then it all gets sealed with heat shrink that we shrink with a heat gun, and that provides an environmental seal as addition to more strain relief. And so that's the finished product for the engine bay harness. That would go into that picture on top of the engine that I showed previously with the fuel rail and the intake and that close-up of the engine bay. So maybe we want to go back and answer a few more questions that I see are popping up. How would you describe the bond amongst the team members? You spend a lot of time together. You spend a lot of time together putting this car together. And so whether you like it or not, they all become your friends. And you just can't beat working for one common passion with a bunch of people that are equally as passionate and dedicated to engineering and seeing the car go fast and all the jokes and shenanigans that happen in the shop while we're putting this all together to kind of help fight the stress and everything. It's a lot of work, and it's impossible to get through all that work without really good relationship with the people that you're working with. Is there max displacement the engine can have? I don't remember the number off the top of my head, Daniel.
700.
It's 710.
710?
710 cc.
700.
I'm pretty sure.
It doesn't
Pretty sure.
matter. They only sell 699 cc engines, so.
There you go.
Most people end up running sport bike engines, which, because of racing classes in Moto 2 being 600 cc's, the highest specific output engines end up being 600 cc engines. And so a lot of people end up running the 4-cylinder 600s. But because the way that they limit power is not really displacement, but actually an intake restrictor, restricting how much air can get into the engine, there's some advantages to running a much smaller single-cylinder engine and then turbocharging to make up for the lost displacement. And so you can actually make very similar amounts of power at the trade-off of higher cost, lower reliability, but significant gains in weight.
Can someone answer the aero kit question?
Justin, can you answer that? How much do you know about time attack?
Can
Yes.
you hear me? Okay. I mean, I think I've seen time attack arrow in that, in terms of the arrow just being crazy and ginormous wings. In that sense, it's very similar, but also we're bound by rules. So there are certain boxes in which we can place arrow. So generally, we just try to make the arrow as big as possible within those bounds. So in that sense, it's pretty similar.
And is there a testing ground on campus we can use to test the car? We go off campus to test a ton of parking lots or on campus that we are allowed to kind of take over. So on the weekends, we go to corporate lots that have given us permission to go there instead.
In terms of, what was it? In terms of aero on the car, big is usually better, and which is why you see these huge wings, but there is also a fair amount of work to make sure that like the front wing doesn't disturb the rear wing. Otherwise, you're just fighting against yourself and you're creating drag, but you're not really creating more downforce. So we'll get now into composites, which will cover a bit more of the wings. Nick, I don't know if you want to talk about this.
Yeah, so the way that we make all of our composite parts, at least for wings, is we have foam cores that we make, and then we hang those cores on a stand like the one in this picture here, and then we cover the cores in resin and lay the carbon fiber up over that, and then those get vacuum bagged and sit overnight so that the resin cures, and then they come out as nice looking wings. So up at the top there, on the top left, is all of the sets of wings from last year's car. We cut them all longer than they need to be whenever we lay them up, and then once they get laid up and are sized and fitted with the end plates, they all get cut down to the proper size, and that's what you can see in the bottom right there. And then once assembly is complete, they all go onto the car, and they look very nice. Next slide, Daniel. So this is a picture from when we had just finished all of the wings. The front wing is obviously in the front. In the rear wing, you can't really see that well, but it is on there. The elements look like they're not all attached at the moment, but yeah, this is what the carbon would look like prior to having all the vinyl attached. So last year when we were making these, we clear coated all of them to make them a little shinier, and although it added weight, it definitely improved the surface finish a ton.
So
Okay, you're saying you can't hear me.
I think most people are able to hear
I've been
you.
able to hear. I think it was a individual tech issue.
Okay.
To answer those two questions that got buried a little bit, there has been a DRS system on the rear wing that has both gone on and gone off the car, as various testing and data simulations proved whether it was or wasn't effective. In the same vein of bigger is better, only if you can prove it. So that's kind of the whole point of this. It's engineering where, yeah, you want to design cool things and you want them all in the car, but then you actually have to prove, does this actually give me the performance gains that I want? And that's a really big challenge because it's not actually as easy to answer as you might think. So,
For the most part, the way that these cars get faster is by getting lighter, which is one of the biggest takeaways you took from Justin writing a lap sim. Throwing aero at it is great, but you do have to always stay on the good side of the weight to downforce ratio, where the amount of downforce you're adding is actually making the car fast enough that the amount slower it's being made by being heavier is overcome. And once we get to the lap sim stuff, I guess that'll get talked about a little bit more. So we'll get now into what is mostly building the chassis, but definitely kind of falls over into some engine stuff as well. I don't know, Justin, if you want to talk about this.
Yeah. So big part of what we do every year is building our own chassis in our shop. So as you can see in the photo, it's sort of in progress, but this is a huge project that we have to undertake every year. And so basically what we do is we receive roll hoops, which are bent by one of our sponsors, and we get notched tubes by another one of our sponsors, and we basically have to assemble it like a giant Lego kit, except for the Legos don't always fit and you have to grind them. So, but it's a lot of fun, and if you enjoy building things, it's certainly a good opportunity. And we also weld the chassis ourselves, so if you're into welding, then this is a great opportunity to learn that as well. So yes, there's a picture of Daniel welding one of the suspension mounts that was really close to the table. So he had fun with that. And Chase, to answer your question, the shop is, I would say, off campus. It's
it's a
pretty
10-minute
close.
walk from Freshman Hill.
So yeah, you can walk, and we also give rides as well. Walking builds character, so that's good.
It's also next to another dorm, so there is a shuttle that does travel there.
Yeah, and here's just another picture of chassis in progress. More mounts on the chassis in that photo as well.
So this is just a quick shot from basically what we get out from all of the data we collect on the car. So it's probably very difficult, if not impossible, to actually read what those axes say. But basically, this is a plot of how much pressure we have in the intake for a given amount of load, or how much force we're putting at the tires, and a given engine speed. And you can see there's that color is very banded. So there's definitely a relationship between those three things. And from that data, we can kind of determine, if we know the pressure in the intake and we know the speed of the engine, then we know how much power it's producing. And so then if you want to go backwards and you say, if the driver applies 60% of the throttle pedal, that means they want 60% of the available horsepower. And so it knows its current engine speed, and it goes, okay, well, what manifold pressure, what intake pressure do I need in order to get to that level of power? And so we can kind of disconnect the direct angle of the throttle and make it more, from the driver's perspective, a more linear experience, and it's easier to drive that way. We still obviously want to leave in some kind of growth in power as the car goes faster, because that just feels natural to most people who've driven cars before. But it's actually something that now with electric cars, a lot of manufacturers kind of fake in, because it just feels very strange to have consistent torque from the time that you start until the time you get to speed. Most people are used to it kind of picking up. The clutch is, well, it's always on the steering wheel, but we've had both cable and electronic clutches. Last year we had a servo that actuated the clutch, and then just a small little thumb lever on the steering wheel that allowed you to use it. We don't use the clutch once we get moving. It's only to start from a stop, and then after that, for upshifts, we just cut ignition. And for downshifts, well, actually now with the electronic clutch for downshifts, we do actually use the clutch, but the driver doesn't have to do it manually. It's all automatic. Justin, if you want to talk about lap sim.
Yeah, so one of the really important tools that we use to determine which direction we want to develop the car is lap sim. In general, it tells us which areas we serve to gain the most from. So this last year, it's something that we very recently brought into the team. So as an example of one of the plots that we can produce from the lap sim, we can see basically these numbers on the contour are the lap times, and you can see how increasing, decreasing the power and mass of the car affect that. And as you can see, the power does not very much, although this is only autocross time, so it's also important that we consider all the other events at competition. But this is a really important tool, like I said, to develop the car, and it's also important to make sure that your model is accurate to how the car actually behaves. So in addition to developing the model, you have to validate that it's accurate. So this is something we're still working on. There's definitely a lot of improvement to what we have now. I know Kevin's been also working on an improved version of what I had. And so if you're interested in modeling, at least the software kind, then yes, this is a great opportunity for getting experience in that.
I guess we'll cover this question now. So Alex asked, is this team led by professor or student led? So we have a faculty advisor who unfortunately is now leaving this year. So we don't actually know who the faculty advisor will be next year. But Jim has always taken kind of the opinion that it's a student club and all the engineering should be student led. All the decisions about club leadership should be student led. And really he just acts as kind of a helping hand and liaison to the administration and EHS and groups like this, so that we can make sure that we can continue to be a part of the RPI community. But in terms of the actual day-to-day running of the team, it's entirely student-led. So around early April, we have rollout and the car gets revealed to the world, and we have lots of pretty pictures and all kinds of happiness and lots of tired. But then we finally do get to go testing. And so this picture here is at actually a local church that lets us use their parking lot. And pretty much we just, we will show up to testing. We try and have plans exactly what we're trying to test that day. Usually you're basically trying to find the sensitivity of adjusting any particular metric on the car to lap time. So you'll iterate through damper settings, or you'll iterate through camber settings and or tire pressure settings, and try and figure out whether or not those relationships line up as you would expect. So we already have a pretty good sense from the math we've done of how those things should behave, but we're making sure that the math and the real world, which are quite different because there's a lot of simplifications made, have the relationship that we expect. It does also tend to end up being a large amount of troubleshooting because of the nature of these cars. There are thousands of parts that go together. But as much as possible, we try and get that stuff worked out on the dyno beforehand, and just do like very rigorous bolt checks and stuff before we actually head out testing. So we don't spend the entire testing time picking up bolts from the ground. So this here is a picture of actually car 2 years ago with a bunch of strings on the rear wing. And the purpose of this was to determine when the airflow was separating from the rear wing and see if it kind of matched the CFD models. And from this, we actually determined, using strings on the side of the car, that the way that we were getting air through the radiators was not as efficient as we hoped. And so we made some changes to that, and we had less issues with overheating, even with less radiator area subsequently. So now the part of the year that everyone looks forward to all year long, competition. So Nick, do you want to talk through this?
Sure. So when we get to competition, first thing that we have to do is unload the 26-foot Penske that we pack the entire shop into. So the car comes out, gets checked over, make sure nothing unfortunate happened on the 14-hour drive to Michigan. And then we prepare the car to go through tech inspection. That's one of the most stressful parts of comp, because the longer you spend going through tech lines, the longer you're gonna have to wait before you can start doing design competition and finishing static events, and then eventually finally getting in the car and driving through the dynamic events. So design is probably the most important event, because it's, for the most part, what we go to competition for. At design, we're given the opportunity to defend every single design that we put on the car to industry professionals, and they are able to give us feedback on our designs and how we presented them and how we can improve on them in the future, and how we can better validate some of our designs. So Daniel, next slide. So this is a picture from one of the events last year. This was the skid pad event. For each event, we have 2 drivers. Skid pad last year was myself and one other driver, Sawyer, who isn't on the call at the moment. But essentially what skid pad is a figure 8 style course. I think it's a 25-foot radius. So we have to do 2 laps around each side of the figure 8. The second lap from each of those is what counts. And essentially what we're testing is the lateral grip that the car produces, and just seeing how fast we can go in a circle before the tires start to break loose. So this is from autocross. Again, we have 2 drivers that run that competition. It's around a 50-second to a minute length course. It's just a cone course that they set up, and the drivers have to weave in and out of the cones without hitting cones or without missing any of them, because I believe hitting a cone is a 2-second penalty, and an off course is a 5 or 10-second penalty.
10 seconds. It may as well be throwing away the thing.
Yeah.
Don't do it.
Yeah. So this is from acceleration. That's a 75-meter dash down the pit lane at Michigan. So I believe that's Daniel in the car right now in that picture.
It's possible.
So
Daniel.
yeah. So for Excel, basically the driver's job is hold the pedal down, don't lift, and keep the wheel straight. So we have a launch control program that we use, as well as traction control to help get us a better launch for when we start Excel. So yeah, I believe the first shift is automated.
No, last year
No?
nothing was automated, but it really
Okay.
because it's like 2 lines of code to make it automated.
Yeah. So yeah, that's another picture from Excel right there. So next slide. Yeah, so this is the team bringing the car to the yearly competition photo. Whenever we're bringing the car around at competition, it can't be running, so we have to push it with a push bar that you can see attached to the main roll hoop, and somebody always has to be in the car steering. And we always have to have somebody with a fire extinguisher both in the car and out of the car, and one person walking on either side of the car so that we don't hit anybody with our arrow. Questions down here. What kind of industry professionals attend the event? So you'll have people from General Motors, Ford. Last year there were some people from Hendrick Motorsports there. They're
4 largest sponsors are Tesla, Ford, Bosch, and Honda, with a variety of other industry names all over the place too.
yeah.
So you get to talk to some people.
One neat thing is like we use different components in the car from like industry and stuff. Like our ECU is from a company called Motec, and at design judging we had like employees of Motec judging us on how we use their systems. So
It was
it's
pretty
really
intense.
interesting to like meet with people who designed what you're using and have to defend why you're using it. To the
Hard to
people who
blame it
designed
on the tool when the person who designed the tool is standing right next to you. But also an excellent tech support because they're standing right next to you. In terms of what language the team typically codes in, it kind of depends. So for stuff like the lap sim, that was all MATLAB, which some people will argue is not programming. And then the actual car is Motec's own language, but it's C-based. And then I guess other stuff, the SAN, the processors for the strain gauges was Arduino. So
Yep.
all
And then all the wireless telemetry stuff was just various scripting in Ubuntu
lots of
distribution.
curly braces. That's a nice picture of us at comp. We stay in a hotel or a motel, the same place every year, and they're very nice to us. But that's just kind of getting some nice rest before we had, I believe, endurance the next day. The car stays at the track during the night, so there's really not much we can do that night other than just everyone fingers crossed and try and make sure the drivers get some good rest. So we'll talk now. I'll let everyone have a few minutes. Actually, let's see how we're doing on time. Yeah, real quickly, kind of speak about why you joined, what the team's meant to you, what you like about it. And then, Alex, when we get to the companies that hire us, if you could talk a little bit about business as well. So we'll go through, talk about why you joined. Kevin, you want to start?
Yeah, sure. So, I mean, I just joined, so I was kind of in the same position as a lot of you guys probably in the presentation right now. I was just kind of looking at clubs. I did robotics back in like high school, so I was looking for clubs where I could get hands-on engineering experience and things like that. And saw this club. I was like, that's neat. So I checked out a few clubs. So I checked up this team. I checked up hybrid. I also checked out the electric vehicle team. And really, this team is the one that resonated with me the most. This team has been amazing. I joined freshman year, fall semester, became a full member in like the spring semester, and then very quickly also became like electrical specialist for a variety of reasons. And Yeah, I mean, I just joined because I thought it was neat, and I am super happy I did because it's been an amazing experience
Nick?
all 4 years.
All right, so I've been around motorsports in some way, shape, or form since I was about 5 years old. So I've been really interested in racing since then. And when I was going around looking at colleges, I went and visited RPI and saw Rensselaer Motorsport tabling at one of the events. And I came over and had a conversation, and it was, yep, that's done. And that was decision made. And I joined the team as soon as I got to school at the beginning of my freshman year, became a full member that November, and I've been here ever since, and I intend to be here until I graduate. So I love this team. I love motorsports, and it's just the almost all of the great memories that I have of RPI so far are linked to this team somehow. So yeah, I'll hand it off to Katie.
So I joined the team by accident. I showed up to the shop because I had two friends that were in composites. And so I just wanted to see what it was about because they were missing for like 3 weekends in a row. And then I turned out, maybe I'll go missing for all the weekends in a row of my spring semester. I changed my major a week after I joined the team from biomedical engineering to mechanical engineering. And I think I set the record for fastest person to go from volunteer to full member. Just because it's just such an exciting area to really learn about why you're passionate about engineering and what engineering looks like outside of your curriculum. And so it's just an inspiring place to be and to learn and explore who you are as a person and then what you'll be as a professional while you're in school.
All right, I don't want to rush anybody along, but it is 2:52, so I want to make sure we have some time for questions. So, Sam, not rushing you.
Yeah, so just real quick, similar to what a lot of other people said, when I was walking around and on my second week on campus, I saw a post that said, hey, electrical engineers and CS and computer engineers show up to a meeting because we really need you guys and there's some cool stuff and we make a car. And it's like, oh, well, that sounds pretty cool. So I guess I'll show up. And then, I showed up to a few meetings and I distinctly remember one of the design meetings for engine drivetrain and electrical. Someone was talking about their going really into depth talking about their design for regrinding the camshafts, and a lot of it was way over my head because I gotta admit, walking to the room, I didn't really know what a camshaft was. So I knew I was really confused, but I also knew that everyone in the room was really passionate about the topic and it was a really interesting subject matter. So I kept coming around, and I found my own way to contribute to the team. And the community of the team, the family of the team is really something special, and that's characteristic of a lot of places at RPI. But I think specifically Rensselaer Motorsport, we build a tight bond.
Justin?
Yeah, so for me, it's pretty simple. I like race cars, I like engineering, and I wanted to get some hands-on experience, so I joined the club. And also another thing was I really wanted to drive the car, but if that's you, don't say it unless you want to get teased. So
But seriously, we're going to need drivers.
I'd also like to note that Justin sent us an email over the summer or something, and we all thought it was pretty hilarious.
Justin was a very involved member from before he stepped on campus, and it was good. You managed to get a step ahead. Alex? So myself, freshman year, well, I guess even before coming to RPI and college, knowing where I wanted to go, I knew wherever I wanted to go, I had to have an FSAE team because it just seemed very new to me, but little did I know at the time just how much work goes into these and just how in depth the design on them is, and just how insane it feels to drive them. They're little rocket ships. I love every single part of it, except for when it lights my computer on fire trying to do Sims, which is why I bought new computer parts that should show up in a few days. Yeah, it's been the dominant part of my experience at RPI. It kind of really brings meaning to going to classes because you get to learn about race car things. It's an excellent way to use your time, and I'd highly suggest it.